So what I'm doing for this project is medical imaging segmentation using token labeling. So as you know, the token labeling is the state right now is the state of the art for the image classification with the transformers. So they've I'm going to introduce this idea, and then I'm going to talk about the problem statement and the motivation. So the problem statement in this project is improving the segmentation performance of the networks for brain tumors. So I'm going to use Brad's data set in this work, and in the literature when I was looking for an idea about the project, I see that a little research is when they use backbones for the image segmentation for the brain tumor, and then they always use train from scratch for image brain tumor segmentation, and then the networks are usually large and hard to train. So the plan is to design a small backbone to using the image tumor segmentation and improve the results. So if I want to introduce the token labeling, they say that all tokens in the image transformers, vision transformers, are important, and then they use a dense score map to label the tokens, and they use a loss function to penalize the classification, wrong classification of the tokens in regard of the dense score map. And then they have a class loss as well. It's in this regard, it's exactly the same as the image transformers. So for the labeling the tokens, they use NF nets, normalized feature nets, something like this, to generate the dense maps. So what I was going to do here was using transformers, because they didn't use transformers for token labeling. So I was doing the I was going to do to use transformers to label the tokens, and the idea for using the transformers to label the tokens is that I'm going to use a discretization method. So shapes have a constant pattern in the patches, so we can use a discretization method to label the tokens in the transformer based label tokening. So if you can learn these patterns in discretization, the output tokens of the transformers is going to be very much informative. So what I'm proposing here is that we freeze pre-trained layer of the transformer. So we have something like a big transformers, a base transformer or large transformers, which is trained on larger data set, for example, ImageNet 21K. And then we define a code book, essentially. So we define N, which is the hyperparameter, random embedding label, as learnable parameters here. So we have it code book, and then we feed our tokens, the encoded tokens, to this code book with, and then we discretize it with the minimum distance. So we get the minimum distance of this minimum distance of the encoded tokens and this code book that we are training. And then we get this labeled discretized label embedding tokens, and we feed it through a decoder, and we use the reconstruction loss to train this codebook. So as you can imagine, if you improve the N of this hyperparameter, this reconstruction loss is going to get lower. But for this purpose, we are not going to do a large number of labels here. So for building the backbone, I did this transformer, but the problem with this discretization idea is it is very hard to train. And because this is not differentiable here, we needed to copy the copy the loss from this section to this section to make it differentiable, and we are able to do the back propagation. So when this step is done, we can use exactly that with the trained codebook and pre-trained transformers, we can generate the dense map to feed to the label tokening transformer. So here I did exactly the same thing, and I used a big transformer with trained on ImageNet 21K, and here I used the trained codebook to label the tokens in token labeling network. And as you see here, with N2000, the number of labels for the tokens. For the ImageNet 1K, I get 80.2% accuracy in contrast to the normal image, the label tokening vision transformers, which is 79.1% accuracy. So I was able to train the transformers and make this work. And the next step for me is to train adding the segmentation head to the tiny vision transformer with the transformer label tokening, and train it to on ADE 20K. And then I'm going to fine tune it on the Bratz dataset and see the results. So that was my presentation. Any questions?